In this video, we're going to talk about IR spectroscopy, infrared spectroscopy. And we're just going to go over the science behind it, some few details, talk about the shape, intensity, wave numbers, some factors that affect the frequencies that you see here. And then we're going to talk about what signals to look at so that you can distinguish, let's say, an alcohol from a carboxylic acid or an alkane from an alkene. And then after that, we're just going to go through a series of multiple choice practice problems so you can know how to look at a graph and immediately tell what functional group it represents. So we'll do that towards the end of the video. And so let's go ahead and get right into it. So IR spectroscopy, it's very useful for determining functional groups. So let's say if you have a structure or a graph in front of you, you can tell if it's a carboxylic acid, an ether, or an ester. Now, when a molecule absorbs infrared radiation, which is just below red light under the visible spectrum, it causes molecular vibrations. The molecule can stretch, compress, or even bend when it absorbs IR radiation. Now, in this graph, on the y-axis, you have percent transmittance. And the number increases from 0% all the way to 100%. Now, transmittance is the idea behind transmittance is the amount of light energy that passes through the sample. So if you look at this signal here, let's estimate that the percent transmittance is around 80%. That means that 20% of that energy was absorbed. 80% passed through the sample. Now, if you look at this signal here, let's say it's at 10%. So if 10% was transmitted through the sample, 90% was absorbed. So that's the relationship between absorbance and transmittance. They're inversely related. On the x-axis, you have what is known as wave number. Now, the units for wave number is reciprocal centimeters. This is around 3,000. That's about 2,000. And here it's about 1,000. So the wave number, which looks like a V with a line on top, is equal to 1 over lambda, which is the wavelength. As the wavelength increases, we know that the frequency decreases. They're inversely related. And as the frequency of a photon decreases, the energy decreases, and so does the wave number. So wave number is proportional to frequency and energy. So the higher the wave number, the higher the frequency of the photon, thus the more energy it has. Now, around 1500, it separates two regions. The right side is known as the Fingerprint Region. And this region, you really don't want to focus on it too much. What we're going to focus on is on the left side, which is known as the Diagnostic Region, also known as the Functional Group Region. The left side pretty much clearly helps you to identify the functional group. The right side tells you the molecule as a whole. It's unique to each individual molecule, just as your fingerprints is unique to you. Now, let's talk about the shape of a signal and the intensity. There's really two ways to describe the shape of a signal. It's either broad or sharp. As for the intensity, you can describe it as weak, medium, or strong. So, how would you describe this signal? Would you say it's broad or sharp? This signal would be broad because it's very wide. Now, what about its intensity? Would you say it's weak, medium, or strong? Now, because it has a low transmittance, which is a high absorbance, the intensity is described as strong. Now, let's look at this signal here. As you can see, it's not very wide, so it's not broad. So this signal would be, it's sharp. And as you can see, it's very small, it's short. Because it's short, it's a weak signal. So it's sharp and weak. Now if we look at the next one, This is not very sharp. It's not thin. So it's somewhat broad. So let's put B for broad. But at the same time, it's very tall. As you can see, it has a high absorbance. So it's broad and strong. Now looking at this signal, how would you characterize it? Would you say it's broad or short? Now you see how it has a sharp edge? This is a sharp signal. This is a broad signal. So we can say it's sharp. And it's not, would you describe it as weak, medium, or strong? So a weak signal is very small. A strong signal pretty much almost touches the bottom of this graph. This is a strong signal. So this signal here is somewhere in the middle, so we're going to describe it as medium. And this last signal, it's strong because it pretty much goes all the way to the bottom. It's about to touch the x-axis, but it's very sharp. If you look at the edge, it's a sharp signal. It's strong and sharp. So those are some ways you can look at a graph and you can describe its intensity and the shape of the graph, or just the shape of that particular region. So now let's look at some other things. So you might be wondering, what causes a signal to be broad? And why are subsignals sharp? Well, most broad signals, they tend to be like an OH or an NH bond. So usually they have hydrogen bonding. And other signals like the Carbonyl Stretch, they tend to be broad as well because it's very polar. By the way, anything that has hydrogen bonds is also very polar. So an OH bond is very, very polar. So these bonds, they tend to be broad. In the case of hydrogen bonding, the reason why, let's say, a carboxylic acid is broad is because all of the intermolecular bonds that are formed between carboxylic acid molecules. So this is the intermolecular hydrogen bond. And when you have those intermolecular bonds, those interactions creates a range of signals in which the sample will absorb infrared, and so that's why it tends to be broad. Same thing with the Carbonyl Stretch. You have dipole interactions. Here this is partially positive, that's partially negative, so these are attracted to each other. And so anytime you have very polar bonds or hydrogen bonds, it tends to be broad. Now, the reason why some peaks are sharp is because they're usually nonpolar, or relatively speaking. And so you don't really have those strong dipole-dipole hydrogen bonding interactions. So that's why it appears to be very sharp. Some typical examples is like the CC double bond stretch or the CC triple bond stretch. This one is like weak and sharp. This one's like usually medium but sharp. As you can see, these bonds are nonpolar, and that's why they tend to be sharp. But now let's look at some other factors that affect the signals. So one factor is the mass. As the mass of the atom increases, the wave number usually decreases. So the carbon-hydrogen bond has a signal around 3,000 wave numbers, or reciprocal centimeters. The carbon-deuterium bond, deuterium is an isotope of hydrogen, but it's slightly heavier. It's around 2,100. For the carbon-carbon bond, it can vary between 1,000 and 1,200, but as you can see, carbon has a higher mass than deuterium or hydrogen. The carbon-chlorine bond, usually around, you could say 600 to 800, this can vary too, but as you can see, chlorine is much heavier than carbon. And then we have the carbon-bromine bond. Bromine is bigger than chlorine, and that's usually around 550, but sometimes it can vary as well. And then you have the carbon-iodine bond, which is even less, 500. So you can see a trend here. As the mass of the atom increases, the wave number usually decreases. Now the next trend you want to be aware of is bond strength. As the bond strength or bond energy goes up, the wave number goes up as well. So as we said, a carbon-carbon bond was around 1,000 to 1,200. A carbon double bond is around, could be like anywhere from 1600 to like 1660. A carbon triple bond, usually roughly around 2200. A carbon nitrogen bond is around the same area, 1000 to 1200. A carbon double bonded to a nitrogen is around 1650. And a carbon triple bond to a nitrogen, a nitrile, that's around 2200. A carbon bonded to a single bonded oxygen, it can be anywhere from 1000, I've seen as high up to 1300. And a carbon double bonded to an oxygen is around 1700. So as you can see, the single bonds are around the same, 1000, 1100, 1200, 1300. They're around that general area. The carbon-carbon double bond is the same as the carbon double bond nitrogen. All the double bonds are around 1700. So they're very close. The triple bonds, as you can see, they're around 2200. So triple bonds have a higher wave number than double bonds, and double bonds have a higher wave number than single bonds. So as the bond strength goes up, the wave number goes up. That's the second trend that you want to be familiar with. Now the third thing you want to be aware of is conjugation. So here is cyclohexene. It has a double bond, and here we have a conjugated diene, and then we have benzene, which is even more conjugated. So this regular double bond is usually around 1650. This conjugated diene is a little bit less, 1620. And for the aromatic ring, it's 1600. And we're talking about the C double bond stretch for each of these examples. And so as you can see, as the conjugation goes up, the more conjugation you have, the wave number goes down. It decreases. They're inversely related. So now let's go over the differences between alkanes, alkenes, alkynes. So in a typical alkane, you're going to see a signal that usually looks something like this. And this is the alkane CH stretch. The signal for this alkane is about 2900. Now for some alkanes, you may see CH2 bend or CH3 bend. So usually this signal would be a CH2 bend, and that's usually around 1400 to 1450. But sometimes you don't have to worry about this because it's in the fingerprint region, but just in case you do. And this one, usually to the right of it, is a CH3 bend, a methyl bend. And that's a little bit less, somewhere around 1350 to 1400. By the way, the CH2 group is known as a methylene group. So now for alkenes. Now there's two types of alkenes that you have to worry about. You have the internal alkenes and the terminal alkenes. So the internal alkenes, that's where the double bond is in the middle of a compound. So you might get something that looks like this. And for a terminal alkene, the double bond's at the end. Now both of these are similar in that they share the same C double bond C stretch, which is around 1660 for like both of them. But somewhere in that range. It could be 1650, 1670, but it's the same for both. Now, the way they differ, the terminal alkene has a double bond CH stretch. As you can see, there are hydrogens here. Now, some internal alkenes may have the hydrogens, but let's assume that we have one that has 4 R groups. In this case, this internal alkene does not have any hydrogens connected to it, so it won't have this double bond CH stretch. But some internal alkenes may have it. But an alkene with 4 R groups, it won't have it. So this double bond CH stretch is usually around 3000 to 3100. So for an alkene, these are the two most important signals that you need to look for to determine it. If it's terminal, it definitely has both. If it's internal, it depends on if there's any hydrogens attached to the carbon-carbon double bond. If there's none, we won't see that double bond CH stretch. But if there's at least one, you still may see it. So like this example, here is an internal alkyne. It has a hydrogen, so we should expect that we should see this signal in the IR spectrum. But now let's say if you have an internal alkyne that looks like this. As you can see, it's a tetrasubstituted alkene. I keep saying alkyne, but tetrasubstituted alkene, and it has 4 R groups. So therefore, it shouldn't have this double bond CH stretch. So now let's go into alkynes. So we're going to compare the internal and the terminal alkynes. So let's start with the internal alkyne, which would look like this. And the terminal alkyne, there's going to be a hydrogen on one side. Now, both groups have a double bond, a C triple bond C stretch. And as a result, they're going to have the signals around 2200 roughly. Sometimes it might be 2100, so we'll say 21 to 2200. So this has it too. Now the internal alkyne does not have any hydrogens attached to the carbon-carbon triple bond, but the terminal alkyne does. So therefore, that's how you can distinguish the terminal alkyne from the internal alkyne by looking at this stretch. And that's usually around 3100 to 3300. So let me show you how it looks like on a graph. So typically you'll have this alkane CH stretch around 2900, which is almost always there. Now for an alkene, you'll see like a signal somewhere to the right of it, and that would be the double bond CH stretch for an alkene, usually around 3100, but 3000 or 3100. And then to the right of that, somewhere over here, you'll see a triple bond CH stretch for a terminal alkyne, which could be anywhere from 31 to 3300. So that's where you'll find those two peaks at whenever you have a graph that you're analyzing. But now there's something else that we need to mention in reference to alkynes, and that's symmetric versus asymmetric alkynes. So let's say if you have two internal alkynes, as you can see, there's symmetry between that triple bond, but for the other one, it lacks symmetry. So we're going to say it's asymmetric. As we can see here, we have a methyl group, and here is an ethyl, so they're different. But here we have two methyl groups which are identical, so that's why we have symmetry. And whenever you have a symmetrical carbon-carbon triple bond, there's no dipole moment, and therefore, if there's no dipole moment, it's IR inactive, which means the C triple bond C signal at around 2200, you won't see it. It won't be there for this particular compound. So anytime you have a symmetric bond, especially when these two elements are identical and these two sides are the same and there's no dipole moment, it's going to be IR inactive. You won't see the signal in the spectrum. Now here, even though these carbon atoms are identical, their electronic environments are different. Here you have a methyl, here there's an ethyl. So even though this bond is still relatively nonpolar, it still has a small dipole moment, so it's IR active. And this signal on the graph, it's actually very small. Around 2200, you might see this weak, very weak signal. And that's why it's so weak, because this bond is relatively nonpolar, but it still has a small dipole moment. But you should still see it though, since it's IR active. But now let's talk a little bit more about polar bonds and dipole moments and things like that. So let's consider carbon monoxide. When carbon monoxide absorbs infrared radiation, it can stretch, it can compress. It can't really bend because it has a linear structure, but for other molecules that have 3 or more atoms, they can bend as well. So how do we know if it's going to stretch or compress? Well, electromagnetic waves like infrared radiation, visible light, UV light, radio waves, X-rays, all of them, they all have an electric field and a magnetic field that's perpendicular to each other. But we're going to focus on the electric field. When you place a positive charge inside an electric field, it feels a force that accelerates it in a direction of the electric field. When you place a negative charge in an electric field, it feels a force that exerts or that accelerates it in a direction that's opposite to the electric field. Now, looking at carbon and oxygen, which of those 2 atoms is more electronegative? We know oxygen is more electronegative than carbon, so oxygen bears a partial negative charge because it pulls the electrons toward itself. And if you draw the dipole moment, it points towards the more electronegative oxygen atom. So when you place this molecule in an electric field that is going this way, or in the direction of the dipole moment, the purple arrow is the dipole moment, by the way. I'm just going to write dp for dipole moment. Will this molecule stretch or compress? What would you say? Well, the carbon is partially positive. So, like any positive charge, it's going to feel a force that's going to accelerate it in the direction of the electric field, so it's going to go to the right. Oxygen, which has a partial negative charge, will feel a force that will direct it towards the left or opposite to the electric field. So as you can see, these 2 atoms, they're going toward each other. So what we have here is compression. So whenever the electric field is in the direction of the dipole moment, the bond compresses, it becomes smaller. And when the bond length decreases, the dipole moment decreases. And as a result, it becomes less polar, so to speak. By the way, the dipole moment is the product of the charge times the distance between the 2 charges. So as the bond length decreases, the distance decreases, and so the dipole moment decreases. But now let's look at the opposite situation. Let's say if the electric field was directed in the opposite direction of the dipole moment. The dipole moment is still going towards the oxygen atom. It's the purple arrow. So carbon will feel a force that is directed to the left or in the direction of the electric field since it has a positive charge. And the negatively charged oxygen atom is going to feel a force that's opposite to the direction of the electric field. And so what happens is the bond stretches. And since the bond becomes longer, the bond length increases, the dipole moment actually increases in response to it. So that's how you know if a molecule is going to compress or stretch. It really depends on the direction of the dipole moment and the electric field. If they're in the same direction, you have compression. If they're in opposite directions, it's going to stretch. But now let's go back to functional groups and the signals that you need to know in order to distinguish them. So let's talk about a carboxylic acid versus an alcohol. So here's the typical structure of a carboxylic acid. And here is an alcohol. There are 2 important signals for a carboxylic acid. There's a massive OH stretch. If it looks that big, and if you see it, immediately you know it's a carboxylic acid. And the signal for this ranges around 25 to 3300. Now there's another important signal for the carboxylic acid, and that is the Carbonyl Stretch, which is a strong signal and somewhat broad, but it's around 1700. Those are the two most important signals that you need to look for in order to identify carboxylic acid. For an alcohol, there's really one main signal, and that's just the OH stretch. It's broad, but not as broad as the carboxylic acid. And that OH stretch is around 32 to 3500, or 33 to 3500, but somewhere in that general area. But that's the main signal that you need to look for an alcohol. Now, there are some other signals in the fingerprint region that could be useful, but the presence of these signals, it's not always a perfect indicator. It's not always reliable, but I mean, it is a decent indicator. All right. The next important signal is the CO stretch. Now, notice that this carbon atom is sp3 hybridized carbon atom. When you have a CO stretch where the carbon is sp3 hybridized, the signal is around 1000 to 1150. Now, for carboxylic acid, it too has a CO stretch, and this carbon is sp2 hybridized rather than sp3. And so the CO stretch for that, it's going to be a little bit higher. So it's around like 1200 to 1300. So when you see that, that's another secondary indication that you may have carboxylic acid. But the most two important signals to look for are these two. And then you could use this third one just for confirmation. So now let's look at the difference between an aldehyde and a ketone. So an aldehyde has a hydrogen next to the carbonyl group, but a ketone has two carbons attached to the carbonyl group. Now the ketone, the only important signal that it has really is just the CO stretch, very similar to the carboxylic acid, roughly around 1700. It might be like 1710, 1715, but I'm going to just go with 1700, keep things simple. Now the aldehyde also has the CO stretch around 1700. But it has something else too, and that is a CH stretch, a carbonyl CH stretch. So that carbonyl CH stretch, also called the aldehyde CH stretch, it has two signals, one at 2700 and another at 2800. But the most important thing is you need to know how it looks like and where it's located. Now keep in mind, most of these organic compounds usually have an alkane CH stretch, which always looks something like this, around 2900. Now the aldehyde CH stretch is going to be to the right of it, but like maybe somewhere over here. And usually there's like two peaks. So this one, the first one, corresponds to the 2700 peak, and the second one corresponds to the 2800 peak. So it's just to the right of the alkane CH stretch, which you almost always will see in every graph. But when you see this signal here, you know you have an aldehyde and not a ketone. Now the next comparison that we're going to look at is the difference between an ester and an ether. And then soon we'll go over like some actual multiple choice examples. So here is how an ester looks like. And this is the structure of an ether, in this case diethyl ether. Now the ester, clearly it has this carbonyl group, which is this broad and strong signal around 1700. But the ether doesn't have that, so that clearly distinguishes these two. But both of them have the carbon-oxygen bond, the C single bond O rather than the C double bond O. And if you look at the ether, it only has sp3 carbons attached to the oxygen. So therefore, like an alcohol, its signal is going to be around 1000 to 1150. If you see only this signal, you know it's an ether, not an ester. Now the ester has two types of CO stretches. The first one, which I'm going to indicate in yellow, this one here. Notice that this CH, that CO stretch, is next to an sp2 carbon. And so that is going to be around 1200 to 1300. Now the CO stretch between this carbon and this oxygen, notice that this carbon is an sp3 carbon. So it's going to be similar to this signal here. So it should be around 1000 to 1150, just like the alcohol CO stretch. So the ester should have both of these signals. Now again, this is in the fingerprint region, so it's not always 100% reliable, but generally speaking, these signals should be there. So if you see both of them, that indicates an ester. If you see just this, you have potentially an ether. So now what about the difference between an amine and an amide? You know, also by the way, something I want to mention. When I went over alkynes, I want to mention this before I forget, I said that alkynes have a signal around 2100 to 2200. Keep in mind, nitriles also have a signal in this area, around 2100 to 2200. And now there are some other compounds that have a signal in this area as well. And one of them would be a thiocyanate group, which is this. That's around 2150. Another example is the isocyanate group, which is 2250, and an alene, which is actually a little bit less, like 1950. Now if you notice, there's a pattern here. This carbon, what do you think the hybridization of that carbon is? Notice that it's sp hybridized. The same is true for this carbon. It's sp hybridized. This one is sp hybridized. That's sp, and this is sp. So typically, if you have an sp hybridized carbon, it's probably going to be around 2000. It could be 2100, 2200, but somewhere in that area. So I almost forgot to mention that, but good thing I remembered. So going back to amines and amides, or amides. What signals do we need to know that can distinguish the two? So first, let's talk about primary and secondary amines. Now this is a primary amine because the nitrogen is only attached to one carbon. And here we have a secondary amine because the nitrogen is attached to two carbons. Notice that the primary amine has two hydrogens. Now, primary amines, they tend to have like a double peak, which is usually around 33 to 3500 in that general range. And a secondary amine usually has a single peak, which looks like this, which is around the same area, 33 to 3500. As you can see, it's in the same area as an OH bond. They both have hydrogen bonds, NH and OH. But the OH, for some reason, is much more broader. Now, a good way to remember this, if you see two hydrogens on an amine, look for two peaks. If you see one hydrogen on it, look for one peak. But just because there's two hydrogens, that really doesn't explain why there's two peaks, though. The real reason behind this is due to symmetric and asymmetric bending. Now, let's say if you have a primary amine. This would be an example of a symmetric stretch, so to speak, because the hydrogens are being pulled away from the nitrogen. They're both being pulled outward from it. So that's a symmetric stretch. If I said symmetric bending, I meant to say symmetric stretch, by the way. And there's another one called an asymmetric stretch, where one bond is pulled outward away from the nitrogen and the other one is pulled inward towards it. So this is a symmetric stretch, and this is an asymmetric stretch. Now, as you can see, there's two signals. One is around probably like 3300, and the other one is around 3400. Now, the symmetric stretch usually requires less energy, and so the wave number is less. So the symmetric stretch is the one that's around 3300, and the asymmetric stretch, that's the one around 3400. Now, on a test, do you need to know this? Probably not, but depending on how detailed your exam is, you may need to know this information. But on a multiple choice exam where you simply have to identify the compound, if you see an NH2 where there's 2 hydrogens, look for this double peak. If you see an NH when there's 1 hydrogen, look for the single peak. But here's the reason why we have a double peak for the NH2. It's due to symmetric and asymmetric stretching. Now going back to the amide, which looks like this, the amide differs from the amine because it has a carbonyl group. And that carbonyl group will see like a strong broad signal at 1700. However, we also have this NH2 signal, just like this one, so we should see a double peak around 33 to 3500. Well, actually, I do need to make one correction. Now, I did say the amide was around 1700, because most carbonyl groups, they're around 1700, but really the amide is actually a little bit lower. It's actually around 1650 to 1690. And there are some carbonyl groups that are higher than 1700, but I use 1700 as just a nice rounded figure. But now let's talk about which ones are lower and which ones are actually a little higher. So most aldehydes and ketones, they're very close to 1700. It could be like 1710, 1720, but around 1700. And then you have an amide, which is a little bit less. That's like 1650 to 1690. And then you have like an ester, which for some reason is a little bit higher, like around 1735. And then you have an anhydride, which, notice that it has 2 carbonyl groups, so it's going to have a double peak. It can have symmetric stretching or asymmetric stretching. So there's 2 signals for the anhydride. One of them is around 1800. That's the asymmetric stretch, which is always a little bit higher. And the other one, which is like 1750, that's the symmetric stretch. And then you have an acid chloride, which is also around 1800. So as you can see, when you have a strong electron donating group, like an amine group, the wave number actually decreases. And when you have an electron withdrawn group, like a chlorine, the wave number actually increases. Now let's talk about why. Now this nitrogen, it can do 2 things. It can donate electron density by means of the resonance effect. If that happens, the carbonyl bond, it loses its double bond character. It becomes more like a single bond. And so a single bond is weaker than a double bond. Now, if you remember correctly, or before, we said a CO bond was like, could be anywhere from 1000 to 1300. And a C double bond O was like 1700. So if you draw the resonance form of this carbonyl, notice that the CO bond is now single rather than double. So that resonance, it loses double bond character, so the signal drops from 1700 to a lower value like 1650. So anytime you add an electron donating group, it goes down. But when you add an electron withdrawn group, like chlorine, which pulls away electron density away from the carbonyl group, the wave number actually goes up. So now, here's a question for you. Why is the ester a little bit higher? Because couldn't the oxygen also donate electrons to that carbonyl carbon? So now, to understand this, let's talk about some periodic trends. Here's carbon, nitrogen, oxygen, fluorine, chlorine, bromine, and so forth. Now, acid strength increases as you go to the right and as you go down across the periodic table. Base strength, base and nucleophile strength, increases as you go to the left and up. So nitrogen is more nucleophilic than oxygen because it's to the left of oxygen. So therefore nitrogen, because it's more nucleophilic, nucleophiles, they tend to be electron rich, and so they tend to be good electron donating groups. So for one reason, so we can see that N is a better electron donating group than O. Now even though both of these groups can donate electron density by means of the resonance effect, both of them can withdraw electron density inductively by means of electronegativity. You see, oxygen is more electronegative than nitrogen. Fluorine is the most electronegative element. It has a value of 4.0. But because oxygen is more electronegative, it's going to pull electron density more than it donates electron density by means of the resonance effect. So overall, in this structure, the O is more of an electron withdrawn group than a donating group relative to this hydrogen. As we can see by experimental evidence, this signal is a little bit higher. So the inductive withdrawal effects of the O exceeds the electron donating effects. But for the nitrogen, the electron donating effects exceeds the withdrawal effects. As you can see, it's a good nucleophile, but it's not as electronegative as the oxygen. But now, if you look at the chlorine here, the chlorine is not very nucleophilic compared to O and N. As you can see, nucleophilic strength increases as you go up and as you go to the right. So chlorine is not a good nucleophile, so it doesn't want to donate any electron density. Its electronegativity is around 3.0, so it's not it's not as electronegative as oxygen, but it's equally electronegative as nitrogen. So it can still pull electron density away, but it doesn't donate electron density as well as nitrogen does. So it's a very powerful electron withdrawing group because it lacks that electron donating effect of a good nucleophile. So that's why we can see the signal is very high. So those are some things to know about carbonyl groups. Most of them is around 1700, but if you have an electron donating group like an amide or even a carboxylate group, because of the negative charge, this is a better donating group than the ester. These donating groups will decrease the wave number, and these electron groups will increase it. Also, if you have, let's say, a conjugated carbonyl group, the signal won't be around 1700. It's actually going to decrease, maybe to like 1680, 1670, sometimes even 1660. But it goes down when you have conjugation. I know we talked about that earlier in the video. But now let's move on to nitro groups. So let's say if we have CH3 and O2, which looks like this. Now, there's really two important signals that will identify the nitro group. And the first one is actually stronger than the second, and it's a little bit broader. This one is around 1550, sometimes close to 1600, but in that general vicinity. And this is a little bit less, usually around 1380. And they both correspond to the same thing, the NO stretch. So if you have a nitro group, those are some things you want to look for. And the last functional group that we need to discuss is the aromatic ring. It's actually very similar to an alkene. It has a C double bond C stretch, which is around 1600. Now, most alkenes, it's around 1660. It's a little bit higher, but because of conjugation, this signal is less. So let me just make a comparison between an alkene and an aromatic ring. Now, both of them have this double bond CH stretch, which is around 3000 to 3100. So you'll see that with an aromatic ring or an alkene. But now, here's where they differ. An aromatic ring also have another signal, a C double bond C stretch at like 1475, and sometimes another one around 1500. So let me show you how it will look like on a graph. So you might see like a medium sharp peak around 1600. That's the C double bond C stretch. And then maybe to the right of that, you might see another peak and a second peak. You might see one at 1500 and another one usually at 1475. So those are some other signals that you'll find on the aromatic benzene ring. So now what we're going to do is go over some multiple choice examples in which you can figure out what is the correct molecule based if you're given an IR spectrum. By the way, this is just the first part of a longer video, and so I guess you can consider this the trailer version. If you check the description page or the description section of my YouTube page, you'll see a link where I have the complete IR video from beginning to end where you can get a lot of practice problems. So check out that link. It is a paid video, but I'll still have some free practice problems that I'm about to go over soon. But if you want more, feel free to click that link and check it out. So here is the first multiple choice practice problem. So go ahead and try this one. Feel free to pause the video and see if you can choose the right answer. So we're given this graph, and how can we use this graph to determine which is the correct molecule that corresponds to it? Now the graph isn't perfect, it's just a rough sketch. So focus on the important signals and see if you can find the right answer. Now if you're taking a test where if you get a question like this, the best way to proceed is by using the process of elimination. Eliminate the wrong answers and then see if you can come up with the right one. Alright, so the first thing that we notice here is we have a Carbonyl Stretch at around 1700, and we have a massive OH stretch. Whenever you see this massive signal, you know it's a carboxylic acid. So let's eliminate anything that's not a carboxylic acid. Well, B is an aldehyde, so that's out. And C is an ester, so it can't be B or C. Now, both A and D contain a carboxylic acid functional group. So what else can help us to distinguish if it's A or D? Also, we could see that we have a C single bond O stretch for a carboxylic acid. This is somewhere between 1200 and 1300. But that really doesn't help us because in both molecules we have the CO bond. But notice that in answer choice D we have an aldehyde. I'm not aldehyde, excuse me. We have an alkyne. That's what I meant to say. And if you remember from our previous section, we mentioned that an alkyne has a C triple bond C stretch around 2200. But notice that we don't see anything in this region. So there's no alkyne functional group present, which means that this can't be the answer. Therefore, by process of elimination, the answer is A. So here's another problem that you can try. So looking at this IR spectrum, which molecule does it correspond to? So the first important peak that we see is that there's a carbonyl group around 1700. And all the answers have a carbonyl group, so that really doesn't help us too much. So what other signals are apparent here that we can use to simplify the answer? Well, notice the functional groups that we have. We have a ketone, we have an alkene, an aldehyde, an alcohol. Now, and we have an ether. So let's look at the aldehyde. In addition to the carbonyl group, an aldehyde have a CH stretch around 27 and 2800. And we see that here. Here's the signal at 27 and this signal at 28. This signal is pretty much always is there around 2900. That's for an alkane CH stretch. So it's found in each one of these compounds. But since we have the presence of this aldehyde CH stretch, we know we can eliminate A, it's not an aldehyde, and D is out too. It doesn't have an aldehyde functional groups, those are ketones. So we've narrowed our answer down to B and C. So now let's look at some other functional groups. B has an alkene and C has an alcohol. Well, there is no OH stretch, which usually should appear in this region. An OH stretch looks something like this. It's very broad. But it should be around like 33 to 3500. But since we don't have that, chances are it's not C. But now let's confirm that our answer is indeed B. If you notice, we have an alkene C double bond C stretch around 1600. And also, there's also the alkene CH stretch, which is somewhere around here, which is close to 3100. So based on this IR spectrum, we can say that B is the answer. We have an alkene plus an aldehyde, according to that graph. So here's our third example. Go ahead and try this one. So is it A, is it B, is it C, or is it D? So let's take a look at the functional groups that we have. So we have an alkyne, we have an alkane, and an alkene. So here is the alkane CH stretch around 2900. It's found in everything because we have sp3 carbons for all of our solutions, so that won't help us. But notice that we have a signal around 2200, and it's like weak to medium, so to speak, and it's very sharp. So usually this signal corresponds to a triple bond, in this case a carbon-carbon triple bond. So we know we can eliminate B, it's not an alkane, and C is out, it's not alkene. And plus, if it was an alkene, we should see a C double bond C stretch roughly around 1660 or 1650, and we don't have that. So we're between A and D. A is a terminal alkyne, it's at the end, and D is an internal alkyne, the triple bond's in the middle. Both compounds are IR active. They lack symmetry. So how can we distinguish between A and D? Because both of them would have this carbon-carbon triple bond. The distinguishing feature that we need here is a signal around 31 to 3300. There is no signal in this area. If there was, it would be a terminal alkyne. That would be the alkyne CH stretch. But due to the absence of that signal, we could eliminate choice A. So since this signal is not there, it has to be choice D. There are no hydrogens on this carbon-carbon triple bond. If you draw the structure, it looks like this. It's a CH3, CH2, carbon-carbon CH3. There's no CH bonds on this internal alkyne. So D is the right answer. By the way, if you want more IR practice problems, check the description section of this YouTube page. I've posted a link to the remaining part of this video. It contains another 15 multiple choice style practice problems, just like the last 3 that you've completed. So if you feel like you need more practice for your tests, feel free to check that out. And that's it. Have a great day.